Tonight, we chase a shadow, not a monster you can see, but a gravitational presence that shapes entire galaxies. It is the unseen hand that holds stars in orbit, sculpts the webs between clusters, and whispers the story of structure in the early universe. We call it dark matter, a name born from absence, proven by consequence. This is the mystery of the invisible mass shaping galaxies. Prologue: what we see when we look. Look up on a clear night and you see a tapestry of lights, stars in spirals, the pinprick glow of distant galaxies, the scattered haze of cosmic dust. But what holds those lights in the elegant shapes we observe is not only what we can see. Beneath the glow lies a deeper architecture, an invisible scaffold of mass that bends light, holds stars in place, and carved the cosmic web itself. We call that mysterious scaffold dark matter, a name born from the fact that it betrays itself only through gravity, not through light. Tonight, we follow the evidence, meet the leading suspects, and trace the long, patient hunt by scientists across the globe. Galactic rotation curves, the first whisper. In the 1960s and 1970s, astronomers measured how stars and gas move inside spiral galaxies. The expectation, borrowed from planetary dynamics, was simple: move farther from the mass and orbital speed should fall. Instead, for most spirals, the speeds flatten out at a large radius. The outer stars orbit as quickly as those much closer to the center, implying there's more mass than the starlight can explain. That discovery, championed and systematized by Vera Rubin and collaborators, showed that disks sit inside vast, unseen halos of gravitational mass. Flat rotation curves are one of the cleanest, most persistent pieces of evidence that something invisible dominates galactic gravity. Clusters and collisions. Gravity and light part ways. If a galaxy's rotation hinted at missing mass, galaxy clusters provided a sharper probe. In collisions between massive clusters, the hot, X-ray bright gas, the baryonic majority, behaves like a slowed, interacting fluid. But when scientists map the total mass with gravitational lensing, how the cluster's gravity bends background light, the peak of mass often sits where the galaxies are, separated from the X-ray gas. The most famous example, the bullet cluster, shows a clear offset. Lensing says most mass is displaced from the luminous gas. That separation is a powerful, visual argument that gravity is dominated by an unseen, collisionless component, exactly what particle dark matter would predict. The cosmic microwave background, a cosmological ledger. Zoom out to the largest scale and the universe hands us a fossil record, the cosmic microwave background, CMB. Tiny temperature ripples in the CMB map encode the proportions of matter and energy in the early universe. Detailed measurements, notably by the Planck mission, give a precise accounting. Only about approximately 5% of the universe is ordinary baryonic matter, while roughly approximately 27% behaves like non-baryonic, cold matter that clumps gravitationally. That cosmological yardstick matches the mass needed to explain galaxy dynamics and large-scale structure. It ties the local anomalies to a global component in our cosmological model. Large-scale structure and the cosmic web, simulations seeded with only normal matter fail to reproduce the filamentary cosmic web, the timing of galaxy formation, and the clustering we observe. Add a cold, collisionless dark component and the simulations align with surveys. Galaxies inhabit filaments, nodes, and halos exactly as the data predict. Weak gravitational lensing maps and galaxy surveys are increasingly precise. reconstructing where mass hides relative to visible light, and the maps line up with dark matter-driven structure formation. Together, rotation curves, cluster collisions, the CMB, and cosmic web mapping form a convergent case. The universe needs a dominant, invisible mass component. See the Dark Energy Survey and early Euclid maps for the newest mass mapping work. Direct detection, listening underground. If dark matter is particulate, there is a direct way to find it. Catch it scattering off a nucleus. That's the mandate of deep underground detectors. Shield the apparatus from cosmic rays and wait for a rare recoil. The current generation, giant liquid xenon detectors and cryogenic arrays have pushed sensitivity's orders of magnitude beyond earlier limits. Projects like Lux Zeppelin and Xenon NT have tightened constraints and excluded large regions of parameter space for canonical WIMPs. Each incremental non-detection is not failure. It is a map of where dark matter is not, guiding the next generation of detector design and theory refinement. Axion searches cavities and novel ideas. Axion hunts use resonant cavities, dielectric haloscopes, and novel sensors to sweep frequency bands where axion to photon conversion would show up. Programs like ADMX have reached sensitivity that touches theoretically motivated regions, while new techniques, quantum sensors, broadband receivers, promise to extend coverage. Success in Axion detection would be transformative. A clear spectral line in a cavity with the expected properties would be a smoking gun for a particle that simultaneously solves a deep QCD problem and explains cosmic dark matter. The case for an invisible, gravitationally active component is deep and multi-threaded. Flat rotation curves, cluster collision lensing, and the CMB's cosmological accounting all point to a gravitationally dominant, non-luminous matter. But the identity of that mass, particle, field, or a signpost to new gravity remains one of science's most profound mysteries. The hunt is global, patient, and creative. Detectors buried deep under rock, resonant cavities listening for whispers from quantum fields, telescopes mapping mass across the heavens, and colliders smashing particles together in search of missing energy. Each null result tightens the constraints. Each new technique opens a fresh window. The silence we hear from laboratories is itself data, and it sharpens the question. If you want the next discovery unpacked and narrated, the experiments, the hopeful nulls, the breakthroughs that could redefine physics, subscribe to Discovering the Unknown. We will follow the shadow until it becomes substance.